इसमें तो सबको ऐड कर देना था ना, ऑटोमेटिकली ऐड होना था ना लोगों को। इसमें तो मैंने इनको ऐड किया है सत्तर को, लेकिन लास्ट टाइम आप लोग ने ऑटोमेटिकली ऐड करने का ऑप्शन रख रखा था। अच्छा, एक और चीज़ है, डॉक्टर निवेदिता ने मुझे एक लिंक भेजा था जिसमें बच्चों के क्वेश्चंस आए थे। वो लिंक है क्या आपके पास?
भेजा था मैंने।
हाँ,
देखता हूँ।
अगर मुझे चैट में वो लिंक दे सके ना तो मैं फिर
मैं चैट में भेज।
हाँ। हेलो, आपने एक लिंक भेजा था ना मुझे?
हाँ,
जिसमें एक बच्चे के क्वेश्चंस आए
हाँ,
थे।
हाँ।
वो लिंक चैट पे आप भेज सकते हैं फिर से मुझे, ताकि मैं उसे खोल के उसके क्वेश्चंस का भी
ठीक है। हार्ड कॉपी चाहिए क्या? प्रिंट आउट
नहीं,
निकाल
प्रिंट नहीं, बस लिंक ही दे दीजिए
लिंक ही
मुझे,
दे दो,
तो मैं
ठीक
उसे
है।
खोल के इसी में देख के बच्चे
ठीक है, मैं अभी भेज दूँ।
थैंक यू। जी, थैंक यू। So link for practice question is not working.
And already actually I have said
you have
yes,
checked
yes,
it,
and
okay.
then actually I have put the announcement also.
Okay,
It is working now, so please check it
Thank
once.
you, thank you.
Yesterday itself, when you told me, that time only I have
Thank you.
checked and opened them.
Thank you, perfect. I'll start the session then. Thank you. Alright students, good morning. Welcome to our second live session. I hope you can hear me. I just need one of you to write in the comment that you can hear me or you cannot hear me. Then I'll know that we can proceed. So I see some of you have already started writing questions in the chat, which is really good. So students, the way we are going to do live session is that you can type your questions in the chat and I will answer them. I'll try to solve them on a piece of paper, which will be available to you afterwards also. And if when I'm solving the question, I want to have a personal conversation with you, I'll unmute you and then we can talk over microphone. Okay, so last week, I believe that a set of practice questions was shared with you on Tuesday. One of you mentioned that you were not able to access the practice sheet. So I have been told that yesterday this has been sorted out. So now you should be able to access the practice sheet. Please practice the practice questions that I have given you. and it might be time consuming, but it is totally worth it. And the point of today's learning session, live session, is to answer your questions that you have from the practice questions that I gave last week. Now I understand some of you have only now accessed the practice questions, so please try them out yourself once, and only when you struggle with some questions I'll come out and I'll help you. Do not ask me to solve them first. Remember, all the tools that you need to solve those questions are given to you already in the classes, in the recorded lectures. I have at least 2 students who have asked me questions, so I'm going to read the question that was submitted by Shashank using the response sheet. By the way, you must have also gotten a response sheet where you can type your questions last week, and if you haven't, then I'll make sure that the response sheet is shared again. Okay, so the first question that Shashank asked was that how to non-dimensionalize systems. So remember, this is a very good question and I want to clarify about it. How to non-dimensionalize system? First thing you want to make sure is that the whole point of non-dimensionalizing a system, a model, is to make sure that there are no units left. So what you want to do is you want to translate your existing model into a form that is dimensionless, which means no variable in your system should have any units and no parameters in your system should have any units. Now there are multiple ways to non-dimensionalize a system. If I give you a system, you can end up with different correct answers. So there is not just one perfect correct answer. The only time when there is one correct answer is when I ask you that, hey, non-dimensionalize it to make sure it looks like this. Then you need to make sure that your non-dimensionalized system looks like how it needs to look like. Okay, I'll give an example. I'll solve an example here, and I hope that example will help you understand how to proceed with non-dimensionalization. So I'm going to share my screen. Okay. Well, I hope you can see my screen now. So I'm gonna practice a question where I'm going to non-dimensionalize a system, a very simple system, and I'm going to show you that there are 2 different ways of non-dimensionalizing the system, and both are equally correct, yeah, and they both will give you slightly different answers, which is okay. So one example that I did in the class for non-dimensionalizing was this very simple example, which is dn by dt is equal to Rn 1 minus n by k. Yeah, so this is a very simple example that I remember talking about in my recorded lectures. How will you non-dimensionalize it? Step 1 should be to understand what are the dimensions in the system right now. So if you look at the left hand side, what is the dimension here on the left hand side? On left hand side we have number by time. So we have to get rid of number, we have to get rid of time. If you look at rate r, in this particular case, the unit of r is 1 by time. The unit of n is number. What is the unit of 1? 1 is unitless. What is the unit of n? Number. What's the unit of k? Number. So n by k is also unitless. Okay? So now what we have is number by time is equal to number by time by number, and then here we have 1 minus n by k, which is unitless. So once you have figured out how the dimensions look in your existing system, the next step is to identify, is there a part of my existing system that is unitless? So here n by k is unitless. More specifically, 1 minus n by k is unitless. Okay, I'm having some trouble writing n. There we are. So this part is unitless. So once you have identified which part of your system is unitless, use that as a cue to substitute your variables. So this becomes my cue to figure out substitution. So 1 minus n by k is unitless, which means n by k is unitless. Now, one rule of substitution is that you only substitute one variable or one parameter at a time. So here we have one variable and one parameter. So we can substitute n by k as a new function, new variable x. And x is unitless. X has no unit. So it's a very good variable for us. If, for example, we had a two-dimensional system and we had a unitless situation where n by a both are unitless, and n is also a variable and a is also a variable, then I cannot substitute as a single variable. I cannot do this. What I'm trying to say is that we have to maintain the number of variables. If my system has one variable, then my non-dimensionalized system should also have one variable. Okay, so now I can decide that n by k can be x, because n is a variable, k is a constant, so I can divide n by k and get x. So now let's make the substitution. If n by k is equal to x, then dn by k is equal to dx. Yeah. Just to clarify, how are we getting from n by k to dn by k? What we are doing is we are taking a very small value of n, a very small difference in n, a very small difference in x. Now we can use these two to substitute in our original model. We know dn is equal to k dx, and we know n is equal to kx. So this substitution can be made in our original model, and what we will get is k dx by dt is equal to r into kx 1 minus x. Okay, now let's look at the units which are left. At every step after substitution, you have to revise your units. 1 minus x is unitless as before, x is unitless, r has a unit of 1 by time, and k has a unit of number, this has a unit of number, and this has a unit of time. So we are still stuck with 1 by time on both left hand side and right hand side. So now here is a fun thing. What we can do is, let's try to get rid of time. Yeah, number is easy to get rid of. So let's try to first get rid of time. By the way, we can cancel k on both ends. So now we are left with dx by dt is equal to rx1 minus x. Now the only dimensional system that we have left is r and dt. R has the unit of 1 by time and dt has unit of time. So 1 by dt is, so let's get rid of time. How do we get rid of time? We have to define a new non-dimensional entity of time. So I know how to do this. I can take r to the left hand side, and now I have dx by r dt is equal to x 1 minus x. So now r dt together are non-dimensional. Think of it this way. R has the unit of 1 by time and dt has a unit of time. When we multiply them, 1 by time into time, we get 1, we get unitless. So dt is a small unit, small part of time, a small parcel of time. So we can say r dt is equal to d tau. Tau is a non-dimensional time. So now what we have is r dt is equal to d tau. A new time variable is being introduced. If r dt is equal to d tau, then tau is equal to r t. Yeah. So now let's make this substitution. Now we have dx dt is equal to d tau by r. D tau by r is equal to r x 1 minus x. Yeah. Now 1 by r is in the denominator. We can take it to the right hand side, and now we are left with dx by d tau is equal to x 1 minus x. Now if you look at this system, left hand side there is no unit, x is dimensionless, tau is dimensionless. Right hand side also, right hand side also we do not have any unit, so right hand side is also dimensionless. We have successfully non-dimensionalized the system. Now let's look at another example where we have options. We have multiple ways of approaching non-dimensionalizing, and both are correct. But I will not solve the whole question, but I will at least walk you through them. So let's look at this second example. By the way, I hope you can hear me. I hope the screen is visible. I'm going to check. Okay, none of you have complained about audio yet and not being able to see the screen, so I think all is good here. Okay, let's take another example. We are still non-dimensionalizing. So the second example, let's say, is dn by dt is equal to, we'll start with the logistic. And then let's add another term here. Okay, so let's say this is a model. It must remind you of a model we have talked about in the class, but it's okay if it doesn't. Now, this is a model. The first step to non-dimensionalize this model is to figure out the dimensions that are existing in the system. Remember, this is very important that you do it, because in the exam you'll at least get some marks for figuring out the dimensions. On left hand side, n has the unit of number. Hashtag is for number, okay? T has the unit of time. Yeah? R, as before, has the unit of 1 by time. N has the unit of number. N by K is non-dimensional. Okay? Now, if we look at this here, what are the units of bn square, a square plus n square? If you look at the denominator, n square has the unit of number square. Yeah? Anything that is being added to number square should also have the unit of number square. So we can say a also has the unit of number square. So a and n both have the unit of number, and a square and n square both have the unit of number square. Okay? Now let's look at the unit of bn square. N square has the unit of number square. What is the unit of b? How will you figure out the unit of b? This is a little tricky. Remember what I just told you a few minutes ago. If two things are being added or subtracted, they should have exactly the same unit. Here we have dn by dt on left hand side, logistic equation minus this third part on right hand side. So the unit of the second part, which is the logistic equation, this part, should be same as the unit of the third part, which is the bn square divided by a square plus n square. So if we look at the overall unit of the logistic equation, the overall unit is number by time, which means the unit of bn square by a square plus n square should also be number by time. Okay, so the unit of b square n square divided by a square plus n square is number by time. We have to find out, no b square, sorry, b. We have to find out the unit of b. This is not very difficult, this is very easy. If we look at the unit of a square plus n square, the unit is number square. So the denominator has the unit of number square. N square has the unit of number square, b unknown, and overall their dimension is number by time. Yeah? So number square will cancel each other, and now we know that the unit of b should be number by time. Okay? So now we have information on all the units. So I'll change the color here. So here the unit is number by time. Here this part is non-dimensional. Rn has combined unit of number by time. R has the unit of 1 by time. N has the unit of number. N square by a square plus n square. This part is non-dimensional because n square dimension is numbered square. A square plus n square dimension is also number square. So they will cancel each other out. And the unit of b is number by time. Okay, so we are clear about this. So now here, if remember, once you have figured out, this is step 1. Once you have figured out the dimensions of each part of your system, the next step is to identify, is there a part in my system that is already non-dimensional? In this model, there are two non-dimensional parts. The first non-dimensional part is here. I'll change the color again. I'll highlight it. Highlighter, yellow. Okay. So one part is n by k. Yeah. The other part is n square by a square plus n square. These two parts are non-dimensional. So what we have here is, change the color again. What we have here is n by k is non-dimensional, and n square by a square plus n square, this is non-dimensional. So here we have the option of using either this part or this part to non-dimensionalize. Both are correct. Both will give you correct answer. Your answer will look different, but both are correct. If we take the first approach, then we can say n by k is equal to x. We have already defined a non-dimensional version of n. We are not going to repeat it. Okay, you either take this path or this path. Don't take both paths. Okay. So if we go by n by k is equal to x, then we know dn is equal to k dx, and we'll make that substitution in this model. Yeah. So then our model will look like k dx by dt on left hand side, since n by k is equal to x, n square is equal to k square x square. We have already non-dimensionalized n into x, so we are not going to define a new variable. Now all that is remaining is to define non-dimensional parameters. So for example, we can get rid of k on each side. So now we have time that is dimensional, and we have these parameters that are dimensional. So we need to get rid of that. We don't need to define a new variable. This is the first approach. Okay. The second approach is going to come from this part of our model. We can decide that, hey, I don't want to define n by k is equal to x. Instead, I want to define n by a is equal to x. Look at it carefully, what's happening here. If we divide both numerator and denominator by a square, we will get n by a whole square, 1 plus n by a square. So we can define n by a as a new variable x. Don't do both. Either do n by k is equal to x or do n by a is equal to x. Do only one of them. Both will give you the correct answer. Once you have defined a non-dimensional version of your n, don't redefine it. In my classes here at IIT Roorkee, I have noticed that once students come here, let's say a student has decided that I'm going to define n by k is equal to x. I'm going to use this one. Let's say the student has decided I'm going to use this one, n by k is equal to x. Then what I have noticed is that once students arrive here, okay, I need to change the color here. Once student arrive here, after making the substitution n by k is equal to x, now they are like, okay, we should also define kx by a as a new variable y, so that this becomes simple. Don't do that. Once you have already defined that n by k is equal to x, you have taken care of the one variable that you have, so you're not going to define more variables. Okay, I didn't want to confuse you, but I wanted to show you how, first of all, how to do non-dimensionalizing by taking a simple example here. And then I wanted to show you that if your model is not very simple, there is an additional term, you might have two options or more than two options on how to proceed with non-dimensionalization. And again, as I mentioned, both are correct. So if it's correct if you go this route, n by k is equal to x. It's also correct if you go this route, n by a is equal to x. Both will give you slightly different looking answers. Okay, I think some of you would be very interested in solving this question. How to non-dimensionalize this further, how to figure out the parameters that will get rid of the dimensions. I'm tempted to help you out here, but I think what I'll do is I will leave this on you. Okay. I will leave this on you for you to figure this out, because it's not very difficult, it just looks difficult. And if you have trouble, then in another live session I can walk you through how to do this. No problem. I think I have actually a recorded part where I show you a similar question in the class, so you can check that out too. So this is your model, and these are your systems that are still non-dimensional. Time, R, bk, and a square plus k square. That's all. Yeah, so it's not going to be very hard. My advice would be, look at here, how can I make least number of parameters and get rid of dimensions in the second term, this term. And once you figure, don't touch x, please don't touch x, just look at bk, a square and k square. And once you figure this out, then you can also non-dimensionalize r and non-dimensionalize time. Okay, let's look at other questions that we have. Okay, I'm going to still go through the questions we have received in the response sheet. Okay, so this is Shashank's question. Okay, the question is, if x is a fixed point, can we check for the sign of f dash x to know the stability of points in all cases for function of any order? For example, if f dash x at the fixed point is less than 0, is it a stable point or unstable point? What if f dash x is greater than 0? Okay, very good question. I don't remember if I talked about this in the class, but let me share the screen again. I enjoy questions when students ask them. Please feel free to use the chat version. Entire screen, there we are. Please feel free to use chat to ask questions. Okay, so the question that we have now is, let me change the sheet. Can we look at the sign of single derivative of our function to figure out the stability of our fixed point? Yes, you can. I do not encourage you to do that in this course, because this course I want it to be more relying on graphical approach, not on calculation, not on the analytical approach. So the question is, let's say I have a function, a model, dx by, need to change the color of the ink. So let's say my function is dx by dt is equal to function x. Okay. Now first step is I want to find out the fixed points. So to find the fixed points, I've said dx by dt is equal to 0. Let's say the fixed point is x star. Okay. The question is, can I derive this? Can I do its first derivative, put the value of fixed point, and see whether this is greater than 0, less than 0, or equal to 0, greater than 0, less than 0, equal to 0, to figure out whether this is stable fixed point or an unstable fixed point. Yes, you can do that, but again, as I mentioned, I prefer you not to do that. Let's take a simple example. So we have dx by dt is equal to x into x minus 1. Okay, so I'll first walk you through the graphical approach, and then I will talk about this approach that Shashank was hinting at, and this actually derives from basic algebra, where we use this to find out minimas and maximas, local minimas and local maximas. Okay, let's look at the graphical approach first. So step 1 is to find out the fixed point. At fixed point, dx by dt becomes 0. So what fixed points do we have? We have 0 and 1. The graphical approach says that draw a phase portrait, and this is a one-dimensional system. So on y-axis we can have dx by dt, on x-axis we can have x. You have two fixed points, 0 and 1. So graphical approach says I want to find out what is the sign of dx by dt to the right of my second fixed point. Between fixed point 1 and infinity, what is the sign of dx by dt? X is going to be positive, X minus 1 is also going to be positive because X is greater than 1. So this will be positive. What happens between 0 and 1? Between 0 and 1, X is positive, but X minus 1 will become negative because X is less than 1. So here we have a negative scenario. Now what happens when our X is between minus infinity and 0? When X is between minus infinity and 0, X part is negative and X minus 1 is also going to be negative. Negative into negative will become positive. So graphical approach says that our model looks like this. Yeah? Positive, negative, positive. Whenever the dx by dt is positive, the flow is towards right hand side. Whenever the dx by dt is negative, the flow is towards left hand side. Now, if you look at the first fixed point, which is x equal to 0, both flow lines are moving towards the fixed point. So this is a stable fixed point. How do we show a stable fixed point? By coloring. Now, second fixed point here is an unstable fixed point. I think somebody is trying to join the meeting. I have met everybody. Okay. Coming back to here, the second fixed point is an unstable fixed point because the arrows are moving away from the fixed point. Flow is away from the fixed point. So this is your graphical approach of figuring out fixed point and their stabilities. Now let's look at the approach that Shashank was referring to, this one. So in this approach, we need to first find the derivative of our model. Our model is dx by dt is equal to x into x minus 1. So what will be the, and let's say fx is equal to x into x minus 1, which is basically x squared minus x. So first is we need to find out the derivative. So derivative will be 2x minus 1. Now we can substitute the the values of our fixed point 0 and 1 into f derivative. So what we'll get is f dash x star. We're going to substitute these values here. So let's do it with when x star is equal to 0. Fixed point is 0, which is we know a stable fixed point. So what we'll get here is minus 1. So here your first derivative is less than 0. This corresponds to a stable fixed point. Okay? Now let's look at what happens at 1. Yeah, which is my second fixed point. At 1 I have 2 into 1 minus 1, which is equal to plus 1, which is greater than 0. So whenever your first derivative will be greater than 0, then we are dealing with an unstable fixed point. So I'll change the color here. Here we are dealing with an unstable fixed point. Here we are dealing with a stable fixed point. The problem happens when the first derivative is equal to 0. Then it's very tricky to figure out whether it is a half stable, half unstable, stable or unstable fixed point. And the reason why it is tricky is because the linearization fails. What we are doing here is we are relying on linearization of our model, converting a non-linear model into a linear model, and we are relying on that. But when it becomes 0, then it becomes tricky. My advice to you would be for exam, for this course, only focus on the graphical approach, which is this approach. Do not focus on this. This is not wrong, it's just not part of this course and not required at this stage. Okay, let's look at other questions. Ma'am, please consider the standard forms of bifurcation for f dash x. Control parameter being r, saddle, transcritical, pitchfork. Am I right? Okay, let me answer this question right away, Shashank, for you and for everybody else. It's true. A model of this form will resemble saddle node. A model of this form will be a transcritical, and a model of this form will be a pitchfork. But not all saddle models, saddle bifurcations look like this. Not all transcritical bifurcations look like this. So I will encourage you not to think of standard forms of bifurcation, but to figure out bifurcation according to the model given to you. Okay? Alright. Next question is, how do collisions of fixed points differ in all these types of bifurcation? Can all bifurcation be reduced to these forms? No, not all bifurcations will look like these forms. These are very simple algebraic forms. These are the basic forms that we use to teach you what bifurcations are. But bifurcations can come in all forms. You mentioned that pitchfork bifurcation occur in systems with symmetry. No, not necessarily. As long as my system does not have imperfection in it, it will look symmetric. Let me show you what the symmetry of pitchfork. So here, for example, in your own question, you have mentioned that Rx minus Kx cube is a form of pitchfork. So let's take the standard form, not standard form, but the easiest form of pitchfork. So let's say I have dx by dt is equal to kx minus x cube. Okay? Okay, you have a slightly different version, so I'm going to follow your version. Kx minus rx cube. Okay, doesn't matter. Both will give me the same answer. Now, my dx by dt, the function fx is equal to kx minus rx cube. Let's see where the symmetry is coming from. If I substitute x minus x for x, what I'll get is k minus x. So f minus x is equal to k into minus x minus r minus x whole cube. So I'll have f minus x is equal to minus kx plus rx cube, which is equal to minus fx. So this is a case where f minus x is equal to minus fx. This is the symmetry I was talking about. This symmetry will fail as soon as I add an imperfection. As soon as I add an imperfection in the model, the symmetry will fail. So symmetry is not really very important. What is important is the wonderful things that happen when we add imperfections. You can check the recorded lectures to see what happens when imperfections are added. By the way, regarding your question on bifurcation, in the previous live session, I did talk about different kinds of bifurcation. What happens when the fixed points collapse into each other, or they disappear, or they switch their stability. So please look at the recordings from the last week to see my discussion on your follow-up question here. Okay. How to look at a system and say whether bifurcation is pitchfork or transcritical? Can we use something like replacing x? Okay, replacing x by minus x is to see symmetry, not to confirm whether it is pitchfork or transcritical. Alright, let's be very clear about it. Even transcritical bifurcations can be symmetric. Even saddle node can be symmetric. What you need to be clear about is how these three kinds of bifurcations differ from each other. My advice would be, please look into the live session recording from last week, because there I took time to explain all the three kinds of bifurcation. Ma'am, from the next question, from remembering the portions, what all must we know? For example, we must know what all assumptions are being taken and why. Thank you. Alrighty, good question. So, for example, when I talk about Gaussian plume model, you should know what the assumptions of Gaussian plume model are. When I talk about, for example, the fill and draw cycles in sequencing batch reactors, you should know what assumptions we are making. I don't need you to memorize assumptions. For example, Gaussian plume model, I'm not going to say list 9 different assumptions. I'll just ask you what are the important assumptions. And the whole point of remembering assumptions is that you know the limitations of your model. If you know the assumptions and you know that your assumptions are not true for a system, you know you can't use that model. That knowledge is important, okay? For example, in case of Gaussian plume model, we made a lot of assumptions. One of the assumptions is that the pollutant is conservative. The other assumption is that the pollutant is, there's only one source of the pollutant. There are no multiple sources of the pollutant. Another assumption is there is no obstruction to the flow of the plume. So we are making a lot of assumptions. We are making assumption that the wind is only blowing constantly in one direction. So we can say that in that particular direction we ignore the diffusion, but in the other two directions we ignore the advection. Which may not always we ignore the dispersion, which may not always be true. The wind can change the direction. The wind can be still. The wind can be very low velocity, and then we can no longer ignore the diffusion in the x direction. So assumptions are important because they help me understand the limitations of the model. For example, the first assumption I stated of Gaussian flow model is that it assumes that the contaminant is conservative. And if you look at the derivation that I did of the Gaussian flow model, this is a very important assumption. And if the contaminant is not conservative, if the contaminant is degrading or turning into other secondary pollutants, then I need to change my model. So I do not require you to cram things, but I really want you to sit and understand that to make this model, what assumptions went into it. Yeah. For example, exponential growth model, the assumption went into it is that the resources are unlimited. So if you are using an exponential growth model and you see that the population is increasing very fast to a very high number, almost unrealistic, you can say, because the assumption is that the resources are unlimited, but this assumption may not be true. That's why my model is behaving weirdly. So I don't want to encourage you to cram the assumptions, but I want you to think about them. And I hope if you think about 6 different assumptions, you will be able to remember 3-4 during the exam. Okay, let's look at the questions you have typed in the chat. Satya is asking, please differentiate about linear and non-linear 2D system for solving. Yes, good. I'll show you an example. Yeah. Okay, I hope you can see the screen and you can hear me nicely. Alrighty, so we have a linear system, we have a non-linear system. Let's look at the linear system. So my linear system will look like this. dx by dt is equal to, I'm just making up model, 2x minus 3y dy by dt is equal to, let's say, x plus y. Okay, so if I write this in form of my characteristic equation, what I have is correct. When you can write in this very simple form, you have a linear model, a linear system. Okay, when you can write in this very simple linear system form, okay, then you already have your characteristic equation written out for you. This is your characteristic equation. So when you want to find out your eigenvalues, all you have to do is, and this is your characteristic equation A, by the way. So what you are left with is this will help you find out the eigenvalues. Solve this quadratic equation and you will get the two values of lambda. Then you can figure out whether you have a stable fixed point, unstable fixed point, or what. Let's do it. Let's do this calculation. Okay, I hope I have not made any calculated mistake here. Okay, let's apply the Sridharacharya's rule. So lambda is equal to plus minus 3, sorry, minus b plus minus b square minus 4 AC. So 4 times 5 is 20 into 1 divided by 2 times of A. So we have 3 plus minus root 11I by 2. So we have eigenvalues in this particular case that are complex. So we are dealing with spirals. We are dealing with a situation where we have a spiral. Okay. So this was a linear system. It was very easy for me to identify the characteristic equation, which is this. It was very easy for me to say, hey, A looks like this, so this is my characteristic equation. Let me find out my eigenvalues. Once I find my eigenvalues, I know that I'm dealing with what kind of fixed point. The fixed point is a spiral in this case. Now let's look at a nonlinear system, and then you can distinguish how they are different from each other. A nonlinear system, instead of having this very clear cut dx by dt is equal to 2x minus 3y, it will look something like this. Dx by dt is equal to, let's say, 2x square minus 3xy plus 4. Dy by dt is equal to x square plus y square minus xy. Something like this, yeah? I'm just making it up. You cannot write this model like you wrote here. You cannot write this it in this form directly. Even if you try, okay, this can be the left hand side, but how will you find out the coefficients? Because this is not linear. So in this case, you cannot find your matrix A, which will give you your characteristic equation. So you cannot find out A very easily, which is your matrix of the coefficients. So what you need to do is you need to first find the Jacobian. First find the general Jacobian. What is your general Jacobian? Saying this is equal to fxy and this is equal to gxy. Okay, so this will give me my Jacobian. So let's find the Jacobian in this case. Jacobian for x, y, let me erase. How do we erase? Okay, good. Oh no. Give me a second, something is not right. I'm having some issues with the paper. Hold on, folks. Oh dear Lord, this is not good. Okay, I'm having some trouble with pointing my cursor, so give me a second, yeah? Briefly, what you need to do is, before the cursor problem can be sorted out, I can tell you that you need to find out the Jacobian, right? So, del f, so assuming that the first model is equal to fxy, and that the second model is gxy, you need to find their partial derivatives. This will give you the Jacobian, a general Jacobian. So what will del f by del x look like? You need to find partial derivative of this one, the first one. I'm going to use the highlighter. You're going to use this, you're going to derive this by del x and put it here. So this will become 4x minus 3y. So here you will have 4x minus 3y. I'm just wildly hoping this works now. Nope, it doesn't work. Okay. Let me call for help and then I will actually solve this and show you. Give me a second. Hi, there is some problem with the.
Yeah, Vivek, sir, madam. Vivek is
Thank you,
going.
thank you.
Yeah.
um, जब मैं इधर लिखने की कोशिश कर रही हूँ, जैसे इधर लिखने की कोशिश कर रही हूँ, तो ये उधर लिख रहा है और पूरा एक सेकेंड पूरा गलत लिख रहा है।
जैसे आप इस पेज पे है ना, तो इसको क्लिक करके अब लिखना।
हाँ सही है।
अगर ऐसा कुछ हुआ तो मैडम इस पे टिक करना है।
ओह ओके ओके, थैंक यू सो मच, थैंक यू। Students, thank you so much for waiting. The good folks here at e-learning center at IIT Roorkee were able to help me. Okay, so let's come back to the Jacobian business. Okay, let me change the color. Here we are, green. So we want to find out the Jacobian for this. So let's do this. So del f by del x is derivative of this model by x. So we get 4x minus 3y. Del f by del y is again partial derivative of the first model but with respect to y. So we will get minus 3x. Del g by del x is deriving the second model but with respect to x. So you will get 2x minus y. And then here del g by del y is deriving the second model but with respect to y. So you get 2y minus x. So once you have figured out the Jacobian, this is your Jacobian. Once you have figured out the Jacobian, you need to find out the fixed points. So we need to go back to our system here and we need to find out the fixed point. Now for each fixed point, you can substitute the value of x and y of the fixed point in your Jacobian and you will get a number here. Let's say a, b, c, d. These are numbers. These won't have x and y because you have substituted x and y for fixed points. So what you're getting is at each fixed point, you will get a matrix like this and this will give you your characteristic equation. You use this as your A. So the difference between linear and non-linear when you're solving it is in linear, you already have your A, matrix A already available to you, which will give you your characteristic equation right away. In a non-linear system, you don't have your A right away, your matrix A. What you do is you find out your Jacobian, a general form of Jacobian, and then substitute the fixed point values in your Jacobian to find out A for each fixed point. Here, you have one fixed point, one A, one set of eigenvalues, one set of eigenvectors. Here you will have a different A for each fixed point, a different set of eigenvalues and eigenvectors for each fixed point. That's the big difference between linear and non-linear 2D systems. Let's look at other questions. In practice question, link not with set. Okay, hold on. There's some more people who want to join. I'll stop presenting. Okay. Folks who have just joined, please feel free to write your questions in the chat. Okay? Okay, Satya is saying a link not with separate questions for practice, it shows only assignment with weak modules. Oh, that's an issue. I'm going to ask my center here to figure this out because I did share practice questions. Okay, how judge, Satya is asking another question. Let's see if I've gotten all other questions in. Okay. How to judge in drawing face portrait in between line and curve, under curve, upper curve and intersection? I got confused. Please explain once again. Satya, I think I know what you are asking about. So I'm going to ask you here, right? Are you talking about how I figure out using subtraction as a way to figure out the fixed points and the stability of fixed points? Is that what you're talking about? You can type in the chat or you can unmute yourself and let me know. I'm going to assume that's what you're asking about and I'm going to get started explaining this.
Ma'am, have you been easy to judge it, ma'am?
Yes? What did you say?
Have you reached the judgment? There is curve is intersection, there is upper the line B under the curve. Have you easily guessed it, ma'am, for solving? or drawing for face rotation.
Okay, okay. I think I understand your question. Thank you so much. You can mute yourself now. I'm going to explain that.
Ah,
Okay?
okay, okay.
All right. So I'm not going to write the equation, but I'm going to answer the question that I was asking. Good question. Good job. So let's say I have a model that looks like this. Some complex system here minus some complex system here. Okay? This can be e to the power x, and this can be, I don't know, sine x. Yeah? Let's say I have a model that looks like this. Dx by dt is equal to ex minus sine x. I have to figure out the phase portrait. I have to figure out what fixed points it has and what are the stabilities of the fixed point. Now, I do not know what ex minus sine x curve looks like. If I knew the curve, all I would have to do is draw the curve on this one-dimensional phase portrait diagram, figure out when dx by dt is positive, when dx by dt is negative, find the stabilities. But unfortunately, I don't know what ex minus sine x looks like. What I do know is what ex individually looks like, and what I do know is what sine x individually looks like. So I know their individual curves, but I don't know their subtraction or addition. In this case, what I can do is, I can say, okay, dx by dt is basically subtraction of sine x from ex. Yeah? So if I know what ex looks like, let's draw what ex looks like. I know what ex looks like, ex. I know what sine x looks like, so let's draw sine x. Yeah? I know what sine x looks like, but I don't know what ex minus sine x looks like. So my actual model is curve 1, not necessarily line Satya. Curve 1 minus curve 2. It can be a line, it can be curve, doesn't matter. Function 1 minus function 2. Wherever function 1 is higher than function 2, wherever function 1 is higher than function 2, there dx by dt will be positive. Think about it this way. I am subtracting a smaller number from a bigger number. My difference will be positive. On the other hand, whenever function 1 is lesser than function 2, there dx by dt will be negative. All I need to find out to make my fixed point is this. When dx by dt is greater than 0, when dx by dt is less than 0. Let me see if there are people trying to join in. This time we did, yes, there are people trying to join in. This time we did not have automatic joining in of students, which has created issues for some folks, but I get a notification every time someone tries to join in. Okay, so what I need to do is I need to figure out when dx by dt is positive, when dx by dt is negative, when it is 0. What will happen if function 1 is exactly equal to function 2? What will happen to dx by dt? Think about it. When function 1 is exactly equal to function 2, when I subtract them, dx by dt will become 0. So, to figure out my fixed points, what I need to do is figure out where these two functions are exactly equal. And where are these functions going to be exactly equal? They are going to be equal at the intersection points. So, this is one intersection point, so this is a fixed point. Another intersection point, this is a fixed point. This is a fixed point. So, wherever the intersection is happening, between function 1, which is ex, and function 2, which is sine x. Wherever intersection is happening, that is my fixed point. Now I have to figure out whether the fixed point is positive, stable or unstable. So let's number these fixed points. So let's say this is fixed point 1, fixed point 2, fixed point 3. I'm only going to find out stability of these 3 fixed points, okay? In example, but it will give you an idea what to do. Changing the color. Okay. So, if you look at the first fixed point, yeah, what is happening to the right side of the first fixed point? The first fixed point is somewhere here. To the right side of the first fixed point, curve 1 is above curve 2. Remember, dx by dt is basically curve 1 minus curve 2, right? function 1 minus function 2. It can be a line, can be a curve, doesn't matter. Function 1 is ex, function 2 is sin x. When ex is above sin x, ex minus sin x will be greater than 0. Right? Ex is above sin x, their difference will be positive. So in this case, to the right side of the first fixed point, dx by dt is positive, which means the flow is going to be towards right side. X is going to increase because dx by dt is positive. Let's look at the left side. On the left side of this fixed point, we are going to the left. Curve 1 is below curve 2. Yeah, curve 1 is here, curve 2 is here. Curve 1 is below curve 2. Curve 1 is below curve 2, which means 1 is less than 2. So if I subtract 2 from 1, dx by dt is going to be negative. So here, since dx by dt is negative, x is going to reduce. So x is going to flow towards left side. Here the flow is towards left side. So what kind of fixed point do I have here? I have an unstable fixed point. Similarly, if I look at the second fixed point, to the right side of second fixed point, the flow is towards minus infinity, it's towards the left side. To the left side of this fixed point, function 1 is above function 2. So dx by dt will be positive and the flow will be towards right side. So fixed point 2 is a stable fixed point. Let's look at fixed point 3. To the right side, we know flow is towards right side. To the left side of the third fixed point, function 2 is above function 1. Function 2 is above function 1. So 1 minus 2 is going to be negative. So dx by dt is going to be negative. So here the flow is going to be towards left side. So this one is an unstable fixed point. In fact, in this case, we are going to alternate between stable fixed points and unstable fixed points. I hope this helped you understand. This is not, it's a trick. It's not a method, it's a trick. Let's say in the last week, I gave you an example which looked, I don't remember the exact example, but it looked something like this. Okay, I don't remember the example, so I'm going to give you this example. Okay, I don't remember if it was exactly this one or the other one. I know what Rx looks like. It's a line passing through 0, 0. I know what Ex looks like, right? It's this curve. But I don't know what Rx minus Ex looks like. So what I can do is, I can first draw Rx, assuming R is positive. Hold on. Let me erase this and start again. Okay. So this is x, this is dx. And then we have a line passing through the center, and that line is Rx. And then we have the second curve, Ex, because I know what Ex looks like. Okay, we need them to intersect. So, give me a second. Oh my God, this is so wavy curvy. I'll start on the new page, fresh page. It's too wavy curvy for my taste. Okay. So the model that I had, the model that I started with, dx by dt is equal to Rx minus Ex. As I said, I know what Rx looks like, I know what Ex looks like, I don't know what the difference looks like. So I'm going to do that. I'm going to figure out how to draw the face portrait when I know what individually they look like. I don't know what they look like together. So here I'm making my x, and here is dx by dt. I hope the curves are not very wavy curvy this time. This is rx. Okay, or it is wavy curvy. And let's say this is my ex. E to the power x. Now, I know that ex looks like this, I know rx looks like this, and in this particular case they are intersecting. So I know one fixed point is here at the intersection, another fixed point is here at this intersection, right? So I know where the fixed points are. Now I have to figure out the stability of the fixed point. So here I have function 1, which is rx, and function 2, which is e to the power x. Yeah. Whenever, because my dx by dt is basically function 1 minus function 2. So whenever function 1 is above function 2, dx by dt is going to be positive. Whenever function 1 and function 2 intersect, dx by dt is going to be 0, fixed point. Whenever function 1 is below function 2, dx by dt is going to be negative because they are subtracting. So I have figured out the fixed point by looking at the intersection, which is where function 1 is equal to function 2. My god. Okay, here. Now I have to figure out the positives and the negatives. So if I look at to the right of the second fixed point, so let's name the fixed point 1, fixed point 2. To the right of the fixed point, function 2 is above the line function 1. Function 2 is above the line function 1. Function 2 is bigger than function 1. So the difference of function 1 minus function 2 will be negative. So the flow is going to be towards left side. Between the two fixed points 1 and 2, the line, the function 1 is above the curve, the function 2. So function 1 minus function 2 or line minus curve is going to be positive. Flow is going to be towards right side. To the left of fixed point 1, function 2 is above function 1. The curve is above the line. The subtraction of line minus curve or function 1 minus function 2 is going to be negative. So the flow is going to be towards minus infinity. So this is a stable fixed point and this is an unstable fixed point. Alright folks, I hope this helped answer the question. Good question by the way. Let's look at other questions. Students, please remember that I have shared practice question. Some of you were not able to access it. So Dr. Nivedita did look at it yesterday and I'll make sure she checks it again. So you should have access to the practice questions. Please practice them. When you practice them, you'll be able to ask better questions in sense that very specific questions. Okay, this question I'm stuck here. Can you help me? So in that case, I'll be able to give you very specific information about how to solve those questions. So I suspect many of you were not able to access because none of you have asked me questions from the practice questions I gave. And I don't see any more questions coming up. So this was an interesting live session, folks. But my dear students, please look at the practice questions, try to solve them. And if you have questions, you can ask the TA using the online NPTEL portal. And if needed, we will have another live session where I'll help you with the practice questions. I can assure you that if you can do the practice questions better and you are confident about them, then you will also be confident when you are writing your final exam. Okay? Since no more questions are there, okay, there is one. Satya has a request. Any chances to attend model exam before the tentative exam? I will look into it. I will have to check that. I'm not sure. I do not know about if NPTEL has a model exam policy. But as I shared the practice questions with you already, I think that should be helpful for you. Alright students, this is all for this week. Please practice the questions and then if you have relevant questions, we can discuss them. Okay. Goodbye. This recording will be available to you, so don't worry about it.